All right, everyone. So this is section 3.2, and this is all about truth tables. So this might be a new thing for you if you've never studied logic before, but it's fun, I promise. So let's talk about it. So you can't believe everything you hear. Chances are you were taught this when you were younger. And it's pretty good advice. In ideal world, everyone would tell the truth all the time. But in the real world, it is extremely important to be able to separate fact from fiction. When someone is trying to convince you of some point of view, the ability to logically evaluate the validity of an argument can be the difference between being informed and being deceived, and maybe between keeping and being separated from your hard-earned money. So in this section, it's all about deciding when a compound statement is or is not true, based not on the topic itself, but simply on the structure of the statement. So we're not looking at what people are saying. What they say may be nonsense, okay? But their structure of their argument could be logically valid. So with logic, you could say something totally irrational factually, but it can make logical sense. So for example, I could say, all doctors are men, my mom is a doctor, therefore my mom is a man. That makes no sense logically. That makes no sense factually. However, logically, it is a logically consistent statement and actually falls under the form of modus ponens, which is a way of just telling when something is true factually. But so stuff like that, by saying my mother is a man, right? Some of those that statement's not factually correct because my mother is not a man, but it makes logical sense. Okay, so there's that. Negation. So according to our definition, a statement is true, either true or false, but never both. So consider the statement P, which is today is Tuesday. If this is a fact, if this is a fact, Tuesday. If it is in fact Tuesday, then P is true, but negation, it's false, right? Meaning it's not Tuesday. So we want to construct a truth table for this. So what we do is we look at the P and we give the two situations that could happen with it. It can either be true or false. Well, the negation is false of true is false, and the negation of false is true. Okay? So there are two possible conditions for the statement. P being true or false, right? And the negation has the opposite truth value. This is called a truth table. Okay, this is the simplest one. P being true and false, and then the negation being the opposite truth value of those. Okay? Now, there are different types of truth tables. So, there's a truth table for conjunction or and. Okay? So recall that a conjunction is a compound statement involved in the word and. So suppose a friend who's prone to exaggeration tells you, I bought a new laptop and a new iPad. The compound statement can be represented symbolically as this P arrow Q, P and Q, where P is I bought a new laptop and Q is I bought a new iPad. When would this conjunctive statement be true? If your friend had made both purchases. Then the statement, I bought a new laptop and a new iPad, would be true. On the other hand, if your friend only bought a new laptop or a new iPad, or maybe neither of those things, then the statement would be false. Okay? In other words, if either both P and Q are false, then the statement P and Q is false as well. So here's the truth table for that. You have P and then Q. And with truth tables, we say true with two things, P and Q, we set it up as true, true, false, false, and then true, false, true, false, true, false. What this does, these 8 things right here, give us every possible scenario that we can have. The case where they bought the laptop and the iPad, both are true. Bought the laptop, not the iPad, one's true, one's false. Bought the iPad, not the laptop, one's false, one's true. Bought neither, false, false. And so the statement P and Q, it's if we have T and T, then we have true. So true and true is true. True and false is false. False and true is false. And then false and false is false. Okay? So with truth tables, they're only, with the and, Okay? With the conjunction, it's only true if both your statements are true. Every other situation, the whole statement is false. With a disjunction, that we can have the same situation, right? But if your friend actually did buy one or the other, then the statement would be true because of the or. Okay? Because of the or, it's more of a forgiving statement. The only way it's not true is if your friend did not buy the laptop and did not buy the iPad, both. So for a disjunction, the truth table of that is true and true is true or true is true. True or false is true. False or true is true. And false or false is false. All right. So here is a more difficult one. It's the conditional one, the truth table. So ignore this. Let P here. I have my own example that I think makes more sense. Let P be I do my homework. Well, I finish my homework. And Q be we will hang out. Okay? So this is the so the P implies Q here is if I finish homework, then we hang out. Okay? That's the conditional statement here, right? When is this false? Well, let's think about it. The way I like to think about it is when is the promise broken? Okay? So let's look at P being true. P being true and Q being true means that I finished my homework and I hung out with you. So for true, true, the third one is true because the promise was kept. Okay? Good. Now, for the second one, it's essentially saying I finished my homework, but I didn't hang out with you. So that's false. That's the case where the promise was broken, which is bad. So that's why that one's false. Now, the next one, it's a little bit tricky, but try to go with me on it. So this one's saying, I did not finish my homework, but we hung out. So, in this one, did they break their promise? No, they did not. Because they never told you what would happen if they did not finish their homework. They just told you what would happen if they finished their homework. Okay? So, the promise is not broken here. Okay? I don't know if it's kept, but it's not broken. And then this one, they're saying, I did not finish my homework, so we did not hang out. Yes, they kept their promise. Okay? Promise kept. Okay? So that's how the conditional statement works. This is how I think about it. When is the promise broken? It's only broken if the person met their end of the deal, but they didn't meet your end of the deal. Okay, so they said I'll finish my homework, then I'll hang out. They didn't follow through on their promise. All right, so that's the conditional statement. All right, and then you have the biconditional, and this one's honestly pretty straightforward. Both of them have to be either true or both of them have to be false. So with the biconditional, true if and only if true is true, false if and only if false is false, false if and only if true is false, and false only if false is true. Okay? So they either both have to be true or both have to be false for them to be true. Otherwise, they're false. The whole statement's false. Okay? And fun fact, P if and only if Q means P implies Q and Q implies P. Okay? So like it has to go one way and the other. Okay? That's how biconditionals work. Which is why it's such a strict, it's the strictest form of logic. Okay? So let's construct a truth table with this. Truth tables are something that is done mostly through practice. It's kind of confusing just looking at the things, but essentially those 5 truth tables I gave you, the negation, the and, the or, the conditional, and the biconditional, those 5 will help you make any truth table that we have. So construct a truth table of not P, well not P or Q. So what you want to do is you want to do your P and your Q. And so you just say true, true, false, false. And then you do true, false, true, false. You always do this when setting up a truth table with 2 values, P and Q. Okay? Now, what you want to do is you want to kind of make this into a puzzle. You want to put the pieces together. We don't tackle this thing all at once. Instead, we see what pieces do we have? Well, we have a not P. So I'm going to draw the not P right here. And then I'm going to do the negation of all my P's. Well, the opposite of this true is false. The opposite of this true is false. The opposite of this false is true. The opposite of this false is true. So I did that from all my P's right here. Okay? Now we have, the only thing we have left is the not P or Q. Now, you want to do these in order. So whenever you think about truth tables, right, and you want to think of the not P, you want to think about this number, this part first, and then this, because directionality, which one, order matters essentially when it comes to logic. Which one comes first? With or, it really doesn't matter, but with and it does. But I'm just making the principle. So we say false or true, and we see what that equals. Okay? Then with this not P, we do the false or not this. We do false or false and see what that equals. And then we do true or true, and we see what that equals. And then we do true or false. And we did this one first because the not P is first here. And then we do or the Q's. Okay? So, false or true. What was that? Well, according to our truth table here, false or true is true. Right here. Then we have false or false. False or false is false. True or true is true. And then true or false is true. Congratulations, my shirt's coming out of there. That's okay. And there you go. That's our truth table. So we're kind of asking, when is this not true? This statement is true in all the areas except when P is true and Q is false. Okay? So that's when this statement, not P or Q, is false. Okay? So think about it. All we worked with is the symbols here. We didn't even give the symbols any meaning. So what this means is no matter what meaning we give to these symbols, no matter what we make P or what we make Q, right? No matter what, that's the statement, whatever we make with this, right? Let's let A be I like strawberries, and, well, let's let P be I like strawberries and Q be I like grapes, okay? The statement is false when I do like strawberries and I don't like grapes, okay? That's what that means. Otherwise, this is true in all circumstances. Okay? So, all right, another truth table. So we have not, P implies not Q. So, not, parentheses, P implies not Q. So, once again, we set up the truth table, PQ. Same deal. true, true, false, false, true, false, true, false. Okay? Now, what we want to do is we want to look at this and say, what should we break down first? I think we should break down the not Q first. So we have the not Q, and that just gives me the opposite truth value, so that's false, true, false, true. But then we have P implies not Q. So P implies not Q, right? So what we're saying is true implies false, right? And then we have true implies true. Then we have false implies false. And then we have false implies true. So what does that give me? So remember, P was first here, so I got all those first ones from this P column, and I got all those second ones from the not Q column. Okay, so true implies false. Well, look at the truth tables for conditional statements. True implies false is false. Okay? True implies true is true. False implies false is true. And false implies true is true. Good. Now we have the last one. We're still not done. We have to negate all that. So negation of P implies not Q. And we're looking at these ones, right? And so we just do the opposite of those. So it's true, false, false, false. So the only way that this statement is true is if P is true and Q is true as well. Okay? Any other way we construct this makes this a false argument. All right. All right, so let's do this one real quick. This one has 3, P, Q, and R. So how do we do one with 3? I'm glad to show you. So with this one, we have P or Q implies R. So we do P, Q, and R. Now, the number of things you're going to have here is essentially 2 to the n. So here we have 2 to the 3, right? Because there's 3 statements here. So what we do is there's going to be 8 that we go down. So what we do is we say true, 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 false, 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 false. And then this one becomes our true, true, false, false. True, true, false, false. And this last one becomes true, false, true, false, true, false, true. Why do we do that? Because now we have all the scenarios that can happen. All 3 are true, 2 are true, 1's false. We have literally every single scenario here, which is why we do this. Okay, so what do we want first? Well, we should do the parentheses first, right? Math tells us that. So we have this Q implies R. So Q implies R. So we have true implies true. What is true implies true? True implies true is true. Then we have true implies false. That is false. False implies true. That is true. False implies false. That is true. True implies true is true. True implies false is false. False implies true is true. And false implies false is true. It's important to memorize your truth tables. I know this because I've memorized my truth tables. I've been doing logic a very, very long time. But you haven't, so you got to remember them. All right, so study hard. All right, and then you have P or Q implies R. So we have this column interacting with this column. And it's the or conditional. Okay, not conditional, but it's the disjunction. So we have true or true, that is true. True or false, that is true. True or true, that is true. True or true, that is true. False or true, that is true. I think that's false or false. Yep, that is false. True or false or true, that is true. False or true, that is true. So this is true in literally every circumstance except when both P is false and Q implies R is false as well, which is the total case of this one. When P is false, P is false, Q is true, and R is false as well. Okay? So yeah, those are truth tables. We're not going to cover the rest of these. Like, I'm not going to do those for you. Okay? So that's truth tables. Let me erase this, and we'll get to our next section. All right, now we're looking at types of statements. Okay? So we want to know whether statements we make are called tautologies, which mean that they're always true, or we want to look at some self-contradictions, when statements we make may never be true. Okay? So those are the types of statements. It's no secret that weight loss is becoming a big business in the United States. It seems like almost every week new company pops up in existence with the latest miracle pill to turn you into a supermodel. A typical advertisement will say something like, use of our product may result in significant weight loss. That sounds great, but think about what the statement really means. If they use the word may result in, it also may not result in any weight loss at all, right? It may result in weight gain, or it may result in turning you into a pumpkin. In fact, the statement could be translated into, you will lose weight or you will not lose weight. Of course, the statement is always true. So, which is why companies do it, because they're not legally liable. If they tell you use of our product may help you, and it doesn't help you, they didn't lie. They didn't tell you anything that wasn't true. So we'll learn about these types of statements. Okay. So in our study of truth tables, last section, we saw that most compound statements are true in some cases and false in others. What we haven't done is think about whether it's true for every compound statement, So consider the statement, I'm going to Cancun for spring break this year. Its negation is, I'm not going to Cancun for a spring break this year. Now think about these two compound statements. I'm going to Cancun for spring break this year, or I'm not going to Cancun for spring break this year. I'm going to Cancun for spring break this year, and I'm not going to Cancun for spring break this year. Hopefully it's pretty clear to you that the first statement is always true, while the second statement is always false, because it's a contradiction, right? Whether you go to Cancun or not. So in the first is an example of a tautology, a statement that's always true. The second is a self-contradiction. Okay? So here's our definition. A tautology is a compound statement that is always true regardless of the truth values and the simple statements that make it up. A self-contradiction is a compound statement that is always false. Okay? So the statement above was easy to tell, right? But what if it's a more complicated statement or a more complicated argument? That's what we want to do. Okay? So we're going to look at these. Okay? So let P be, I'm going to a metal concert, and Q be, I wear black leather. For the statement below, write the first statement in words using the given statement for P and Q, and try to predict whether it's a tautology, a self-contradiction, and build a truth table to decide for sure. Okay? So P and Q implies P. Well, in English, okay, that's saying if I go to a metal concert and I wear black leather, then I go to a metal concert. Okay. Is that statement always true? I think it is, because you're saying if I go to a metal concert and I wear black leather, then I go to a metal concert. Pretty straightforward, right? Okay, now this one says P and Q and not P and not Q. Okay, so this one's a little bit more awkward, but essentially it's, let me just say it in words. I'm not going to write the whole thing out because it's just a lot, but essentially it's saying if I go to a metal concert and I wear black leather, and I don't go to a metal concert and I don't wear black leather. Yeah, that's that sounds like something that that will always be false. Okay, always be false. And then this one says, I wear black leather, or I'm sorry, I go to a metal concert or I wear black leather implies I go to the metal concert. Sorry, implies I wear black leather. Is that true all the time? I guess we'll find out. So let's draw a truth tables for this. For these. Spoiler, the second one's actually kind of a lot, but we'll get through it. Okay, so this one, we want to do P, Q. Thank God there's no R's, right? So P, Q, so we have true, true, false, false. True, false, true, false. Okay, so we want to do the P and Q. So we have true and true is true. True and false is false. False and true is false. False and false is false. So then we want the P and Q implies P. All right. So we need this column first. So we have true, false, false, false. Implies P, which is either true, true, false, false. So true implies true is true. False implies true is true. False implies false is false. And false implies false is false. And look at that. We have T's all the way down. And therefore, this is an example of a tautology. Okay? So this is an example of a tautology. All right. I think my yellow is giving up. Let's try blue. So the next one, we do P, Q. So true, true, false, false. True, false, true, false. So we want to do not P, and then not Q, and then we want to do P and Q, and then we want to do not P and not Q, and then we can finally say the P and Q and not P and not Q. That's how we're going to construct this. Okay? So if you see any negations, you always want to write those down first. You don't want to like just do them along with something like this, okay? You want to kind of work it slowly. So not P would be false, false, true, true. Not Q would be false, true, false, true. P and Q, so we have true and true, which is true. True and false, which is false. False and true, which is false. False and false, which is false. And then we have not P and not Q. So we have false and false, which is false. False and true. I'm sorry. False and true, which is false. Then we have true and false, which is false. Then we have true and true, which is true. And then we have the conjunction of these two statements, essentially. So we have the true and false. Well, that's false. False and false is false. False and false is false. False and true is false. So the statement is always false, meaning it's a contradiction. It's a self-contradiction. Now, this next one's not that bad. If you would believe me, I won't do it, but here, let me do this. I'll say that it's true, false, true, true. That's what it's going to look like at the end. And I'll let you figure out how we got there. Okay? I can't be doing everything now. Okay, so that's good. So one thing we want to do now is look at, so there's all different types of statements that you can make apparently, right? Like look at everything that we've done a truth table for so far, right? There's all different types of arguments you can make in these weird symbols, right? How do we know if one symbol is equal to another symbol? That's called two statements being logically equivalent, okay? So consider the statement P implies Q and not P or Q. What we see is that the truth table of not P or Q is true, false, true, true, which is the same thing as P implies Q. Don't believe me? Last section. P implies Q has the table true, false, true, true. So these are both logically equivalent statements because they give the same truth table. Okay? They give the same truth table. So two compound statements are logically equivalent if and only if they have the same truth values for all possible combinations of truth values for the simple statements that compose them. The symbol for logically equivalent is like this equal sign, but it has 3 lines. Okay, so for example, we see that P implies Q is logically equivalent to not Q implies not P. Okay, so we know what P implies Q looks like, right? But now let's look at not Q implies not P. So let me erase this so we can show that. We already see what P implies Q is, so I'm just going to do not Q implies not P. Okay, so we have not Q implies not P. So let's do that. We have P, Q. We have true, true, false, false, true, false, true, false. So we have not Q right here. Let's do not P. No, let's do not Q. We have not Q, not P. And then we have not Q implies not P. Okay. Not Q, that is false, true, false, true. Not P, that is false, false, true, true. And then we have false implies false. Well, that is true. False implies, true implies false. That is false. False implies true. That is true. True implies false. Did I do that one wrong? True. Let's see, not Q. True, true. Yes, that's supposed to be true right here. Yep. True implies true is true. Good. And this has the same truth value as P implies Q. So not Q implies not P, right? So let's think of the statement. If I finish my homework, then we will hang out. Is the same logically as saying, if we do not hang out, then I did not finish my homework. All right? They're the same statements logically. So you could say things many different ways, and they mean the same thing. Now, the statement P or Q is logically equivalent to not P and not Q. And the statement P and Q is logically equivalent to not P or not Q. Now, these are the same things as De Morgan's laws, okay? So essentially, we have De Morgan's laws for logic as well. So I think that's really cool. Because essentially, I told you all last time, like set theory and logic are just two halves of the same coin. Okay? So, there's that. So we want to be able to negate some statements. So write the negations of the following statement using De Morgan's laws. Studying is necessary and I am a hard worker. Well, that's the same thing as saying, so this is P and Q, right? So it's the same thing as saying, so there's an and in there. So it's saying studying is not necessary. Or I am not a hard worker. Okay? Those say the same thing. B, shoplifting is a felony or a misdemeanor. The negation of that, so P or Q, is shoplifting is not a felony. Felony, if I can spell tonight. And not a misdemeanor. Okay. So those are two examples. I will leave the rest of those to you, right? Because I think practice is important with this stuff, right? But that's negation using De Morgan's laws. It is pretty straightforward, to be honest. You just got to know which one to use for which. But if you have an or, you turn both into a negation and you switch it to an and. If you have an and, you switch both to a negation and you have an or in the middle. Okay, that's how it works. Another thing that can be shown, the negation of P and Q. We can show that that equals P by De Morgan's laws. We can show that that means P and not Q. We're not going to show this through a truth table, but we can show it. So here's a table showing some statements, P and Q, and its negation and what it looks like, what its equivalent negation looks like. So P and Q, its negation is not P and Q, and that's equivalent to not P or not Q. P or Q, its negation is not P or Q, and that is the same as saying not P and not Q. And P implies Q, that's the same as not P and implies not Q, and that's the same as saying P and not Q, which is what we shown above here. Okay. So variations on the conditional. This is the idea of a of the converse, the inverse, and the contrapositive of a statement. So my conditional statement, so my original statement, right? Like if I get my homework done, then we'll hang out. The converse of that is just flipping the P and Q. It's saying if we hang out, then I will finish my homework. Okay. The inverse of that is when you negate both of them, but you don't change their directions at all. So the inverse of that statement would be, I will not finish my homework. If I do not finish my homework, then we will not hang out. Okay, that's the inverse. The contrapositive of that statement, it's a weird word, but it's an important one, is if we do not hang out, then I did not finish my homework. Now, funny enough, this one and the fourth one, so the conditional and the contrapositive are equivalent statements. Okay, and that can be shown via truth table and stuff. All right, so we'll write the contrapositives. Well, we'll write what those are and stuff, and then we'll call it quits for this section. Okay. So the conditional is if you earned your bachelor's degree, then you get a high-paying job. So it wants you to write the converse, inverse, and contrapositive. So the converse of that is, just make sure I get it so that I don't say something dumb. All right. Where are my notes? Flipping through them everywhere. Okay, so the converse is if you got a high-paying job, right, then you earned your bachelor's. All right. The inverse is if you did not earn your bachelor's, then you do not have a high paying job, right? Which is nonsense, right? Like, so that's what I mean by statements can be logically correct but factually wrong. Okay, contrapositive. So remember, we flip it and then we negate both. Okay, so that is if you do not have a high paying job, then you did not earn your bachelor's. Okay? All right. Now, this one is just asking us to write this using words and stuff, right? So this one's saying in symbols. So if a building owner uses solar heat, the owner will pay less for electricity. That is a P implies Q statement. Using less electricity is necessary for the building of solar heat. That is also a P implies Q statement. A building uses solar heat if the owner pays less for electricity. That is also a P implies Q statement. This one is as well, and this one is as well. Okay. I want you all to try to figure out why they're all P implies Q statements, but these are all conditionals. They are all saying the same thing, just in different ways. Okay, awesome. All right, last one, 3.4. Ironically, this one has like the most, but I'm covering the least. So take that how you will. We won't cover all of it. Only the parts that I think are important. Okay, so this is logical argument. So this is kind of like the culmination of everything, right? This is what we're leading to. Teaching us if our arguments that we make are valid. Okay, how do you know you make a valid argument? So the work we've done in building the basics of symbolic logic in the first 3 sections of the chapter has prepared us for the real point, analyzing logical arguments objectively. That's the topic of this important section. Remember that we're using letters to represent statements. Your goal is to ignore the topic of the argument and simply focus on whether or not the conclusion can be reasonably drawn from the preliminary set of statements. Check your emotions and opinions at the door and get ready to be argumentative. All right. So a logical argument consists of 2 parts, a set of premises and a conclusion based on those premises. The premises are statements that are offered as supporting evidence for the conclusion. Our goal is to decide whether an argument is valid or invalid. When is an argument valid? An argument is valid if the conclusion necessarily follows from the premises, and invalid if it is not valid. An error in reasoning that leads to an invalid argument is known as a fallacy. So essentially what we want is we want a tautology. If we have a tautology for our argument, then our argument is valid. If our argument has at least one part, right, that where it's false, it's not a tautology, then it is not valid. Okay. So notice that our definition of valid doesn't doesn't use the word true, because logic does not care, is not about deciding that the claim is true. It's about deciding if the claim can be deduced from the premises. Let's look at the example. All students in this class will pass. Rachel's a student in this class. Conclusion, Rachel will pass. Since we're told that all students in this class will pass, we can be sure that if Rachel's a student in the class, she will pass. This is an example of valid argument because the conclusion logically follows from the premises. But what could be something wrong here? Like, will every student pass this class? Right? Is there even a student named Rachel in this class? So if one of those two premises are false, then the whole argument is false. Okay? All right. So there's that. So the truth table method. So what we do is essentially we take the premises. And we conjunction all the premises together and make a truth table about it. And then our conclusion, we take all those conjunctions and we draw an implication to the conclusion. All right. I'll show you what that looks like in a little bit. Okay. So decide if the following is a valid argument or not. Okay. So if the ad campaign is a success, the marketing manager won't lose her job. The marketing manager lost her job, therefore the ad campaign wasn't a success. All right, is this valid? So we need to give letters to these, right? So we're going to let P be the first one, right? Which was the ad campaign is a success. All right, and we'll let Q be the marketing manager lost job. So, how is this argument set up? It's set up like the following. If the ad campaign is a success, then the marketing manager won't lose her job. So that is a P implies not Q statement. Then what happened? Well, the marketing manager lost her job, so that's Q. Therefore, and you could draw this like 3 dots right here, that means therefore, not P. So our job now is to make a truth table of this. So what this looks like as actual logic is P implies not Q and Q imply not Q. So this is what we're making the truth table about. Okay, that's our truth table. So let's do it. So we need P, Q, true, true, false, false, true, false, true, false. Okay. Checking the time. Good. Okay. So what do we need? Well, we need a not Q. So that's false, true, false, true. Then we need P implies not Q. So P implies not Q. True implies false is false. True implies true is true. False implies false is true. False implies true is true. Okay? Then we need P implies not Q and Q. So we need false and true, true and false, true and true, and then true and false. Okay? So, true and false is false, true and false and true is false, true and false is false, true and true is true, and true and false is false. Okay? Now we're saying that this big one, P implies not Q and Q imply not Q. So we have this false, false, true, false, and we're saying that that implies my not Q. So false implies false, false implies true, false, true. Okay, so what does that equal? False implies false is true, false implies true is true, true implies false is false, and false implies true is true. So therefore, actually, what did I do wrong? This should all be true. False, false, true, false. Okay. False, true, 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 true. False, true, false, true. True implies false. I think I made a mistake in my notes somewhere, but regardless, this is what I got, so that's what I'm keeping, because I actually did the work myself here and not looked at my notes. So that's what we have. So this is not a valid argument, okay? Why is this not valid? Well, there could be other reasons the marketing manager lost her job, right? Maybe there was a shortage of some kind, right? So there's other reasons why that marketing manager could have lost her job, okay? In this case, it's the case where the ad campaign was a success, right? And the marketing manager still lost her job. Okay, so there's that. So that's how you construct these. These get really big, as you could probably tell. All right, we're going to skip this. And then we're just going to do this one with 3, okay? We're going to do this one with 3, and then we're going to call it quits, okay? So this one doesn't even have any words. It's just all symbols. So we're going to look at these symbols and determine whether it's true. If this form of argumentation is true. So it really doesn't matter what P, Q, or R mean in this case. All we're looking at is the structure, okay? So really what we're trying to do is say, okay, P implies R, and Q and R and P, all of that implies not Q implies P. That's the truth table we're building. It's a big one, but you all can handle it. You're smart. Okay, so let's do this together. So we want P, Q, R. So there's 8 of them now. So we have true, 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 false, 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 true, true, false, false, true, true, false, false. Then we have true, false, true, false, true, false, true, false. Okay, so we're looking at these. So we have the P implies R. We have Q and not R. We have Q and R, and then P, and then we have this not Q. So we need a not Q. So we'll do a not Q real quick, which is just false, false, true, true, false, false, true, true. 2, 4, 6, 8. Good. We have 8 there. Okay, what else? Might as well give myself the rest of it. Well, then we want to start doing this. So we want to start doing the P and R, the Q and R. So let's do the Q and R. Well, let's do the P and implies Q. So we want to do P implies R. And here we have true implies true, which is true. Then we have true implies false, which is false. True implies true, which is true. True implies false, which is false. False implies false, which is true. False implies true, which is true. False implies false, which is true. I'll just copy my notes here because I'm not. Then the last one's true as well. We have 4 truths there. Okay, good. All right, and then we have Q and R that we want to do. And that's going to be true, false, 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 true, false, false, false. Okay? Well, now we want to do P implies R and P implies R and Q and R and P. Okay? So that's kind of doing 3 at once and stuff, but we can handle it, okay? So that's going to give us true, false, 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 false. And once again, check it for yourself and see why it's true. And then all of this in here, okay, in this spot, that is a complete tautology. So it's a logical argument. Whatever you make P, Q, or R in there, it will be a logical argument. All right, that's all I really care about with this. If you can, finishing it up, if that you can do this, okay? Make these logical arguments and stuff. You'll get practice on your homework, all right? They are big, I'm sorry. This one's huge though, okay? So they don't usually get this big, honestly. With that said, this is my last video for you all for this week. Study hard. If you need my help, I am very available. So yeah, email me and we will surely chat. Thank you all.